Kia ora koutou, no mai, haere mai. Welcome to lesson 36 for introductory physics. This is the last lesson for this course. What we're going to do in this lesson is look at mirrors and lenses. So we're going to take the ideas we've already met around reflection and refraction and the ideas of electromagnetic light, what we understand about that, and we're going to apply them together. We're going to put them together and we're going to see what happens. So we're going to understand how lenses and mirrors work. So our goals are to, first of all, talk about reflection a little bit as it relates to diffuse and specular terminology. So that was a weird way to say what I just said. We're going to define those terms. We're going to talk about the law of reflection. So when we talked about reflection of other waves, we just sort of talked about it as a phenomena that occurs. We didn't put any kind of quantitative analysis over that. So we're going to do that. We're going to talk about ray diagrams for mirrors. We're going to apply Snell's law to refraction, which, as you'll remember, is the bending of a wave. We're going to talk about dispersion and how that relates to rainbows. Then we're going to move on to lenses and talk about converging and diverging lenses, but we'll also look at pinhole cameras, which are a type of lens, even though they don't have a lens. And then we'll talk about real and virtual images, and again, ray diagrams. We want to understand how to draw ray diagrams for different lens scenarios, not just for mirrors. And we'll see the lens equation, which will again bring some quantitative numbers into some lens scenarios, being able to figure out how far away an image will appear on a wall from a lens if you've got an object a certain distance, things like that. So that's our goals for this final lesson. First of all, reflection and mirrors. We've already talked about reflection. We talked about the idea that the energy, remember a wave is just energy being transported through space, the energy will bounce off a surface and go back the way it came. That's a reflection. And that includes light. It works with light as well. And we already talked about the idea of metal reflecting light really well. A shiny piece of metal will reflect light like a mirror. But there are different types of reflection. For most materials, this is what we talked about when we talked about seeing an object. We talked about a book, a white book, reflects photons off in every direction. That's called diffuse reflection. Diffuse reflection is where we just have photons being spread off in every direction. So the incoming photons might be nicely ordered. They might be coming from the sun, which you remember is perfectly parallel, or they may be coming from a bulb and be a light bulb and be circular or spherical. But when they hit that object and reflect off it, if it's diffuse reflection, which most things are, then it will bounce off in all different directions. And because of that, we can see the object that's doing the reflecting rather than where the light came from. When the light stays organized, when it stays ordered, when every light ray coming in parallel will bounce off and still be parallel afterwards, that's called specular reflection. So specular reflection is what everyday language means when we say reflection in that scenario. So if you're talking in everyday language and you say, I can see my reflection, you're talking about specular reflection, this idea that the photons coming in, hitting the mirror or the window, are bouncing off and they're still staying in order. And that's why you can see that object through the reflection, because of course, all light of everything that isn't a light source is reflected. So that's the difference between diffuse and specular reflection. When we talk about this book that we were talking about last time, we talked about the book appearing white because it reflects all the photons. Now what we're talking about is the idea that it reflects the photons in every direction. It does that diffuse reflection. So if we moved around the room, we can still see that book because there are still some photons that have been bounced off that book. So the photons all originally came from the light bulb. They all came from the light bulb, assuming we're in a closed room and that's the only light source. The photons all came off that light bulb. They all hit that book, but then they bounce off in every direction because it's diffuse reflection. And so no matter where you stand, you can see I've drawn two eyes at different positions here, but you could put your eye anywhere in that room. No matter where you go, you can see the book because some of the photons are bouncing off the book in that direction. So they're literally bouncing in every possible direction and filling up the room. So no matter where you go, you can see those photons coming off the book. If instead you have a mirror, that mirror won't send photons in every direction. It won't send rays in every direction. It'll send them only in a nice ordered, organized reflection, that everyday language version of reflection. So that means if you wanted to see that light bulb directly in the mirror, you would have to go and stand in one of the specific locations where the light rays coming from the light bulb are bounced off the mirror and get into the right position for you to see it. So you can see this eye in the bottom right hand corner can't see the light bulb in the mirror because there's no light ray that can come off that light bulb, bounce off that mirror and hit that eye, right? There's no path for that light to travel. But the light ray, the eye that's further up in the center of the image, they can see the light bulb because there is a path from the light for the photon to travel down, bounce off the mirror, and as we'll see in a moment, it has to bounce at a certain angle, bounce off that mirror and then travel to the eye. So that person can see the light bulb in the mirror, the other person can't. They can still see the light bulb directly because there is a path from the light bulb directly to the eye, but they can't see it in the mirror. The law of reflection, as I just said, is the rule around the angles that the light rays can bounce at. For the law of reflection, we always work with the normal. We always work with the normal. That is the same definition of normal as we saw earlier in the course in mechanics and everything. Normal literally just means perpendicular to the surface at that point. When the mirror or surface is a flat, straight line, the normal is going to be, the normal anywhere would be parallel to any other normal. The normal will always point in the same direction. The reason we use the normal is because if you deal with a curved surface, so a curved mirror, then that normal will change. I'll just show you what I mean. It's not required knowledge per se for this course, but it does reinforce the idea of why we use the normal. If you have this as your surface, assuming that was a straight line, I didn't quite draw it straight, but assuming it was, then no matter where you draw your normal, right, it's always 90 degrees, but all of these normals will be parallel because the surface is just one flat straight line. So these normals are all parallel, right? They're all parallel. But if you have a curved surface, then your normal here will be at right angles to that bit of the surface, whereas your normal here will be at right angles to that bit of the surface, and so on. So your normal will be in a different position each time. And that's why we use the normal when we're talking about the angle of incidence and angle of reflection, which I will define now. So always deal with the normal. Once you have the normal drawn on, at the point where the incoming light hits the surface, you draw your normal. So here's your incident ray. Incoming light is just called incident light. So incoming or incident. Where that hits the surface, you draw your normal, and the angle between that incoming ray and that normal has to be the same as the angle between the reflected ray and the normal. Right? So that's all the law of reflection is. It's just saying that that is symmetrical. The light coming in will bounce off at the exact same angle as it came in. But we always work with the normal, as I said, because that way our results generalize to curved surfaces, not just flat ones, even though for now we're pretty much going to deal with flat, although I will mention curved ones. When we see an object, we've already talked about the idea that you can see an object because it's reflecting photons, but how do we know what the shape of the object is? Well, we know the shape because our eye can see where all that color photons come from. If I hold up a piece of paper, then you can tell the shape of this because there's a photon coming from here, photon coming from here, and from here, and everywhere in between. And so your brain knows that that set of photons that are all looking the same, they're one object, and your brain processes it as a single object. That order, that organization of the photons, of all the rays coming from that object to your eye, they are what tells your brain what shape that object is. So the light rays have to be organized for us to be able to see the object. That's how we can see it. And if they didn't, all those bits of paper didn't send organized rays towards you, then the brain would just get this jumble of information. We'd be able to tell nothing about the world around us. So it's the order in all of those rays that allows us to actually see things. For the same reason, when you look in a mirror, you can see the objects that are the rays are bouncing off the mirror, because as they bounce off the mirror, that law of reflection means that all the angles coming in are the same as all the ones going out. So all the rays that are ordered on the way in are still ordered on the way out. So for specular reflection, the order is maintained. For diffuse reflection, we lose that order. They bounce everywhere. That's why when you look at a book, you don't see a reflection of the light bulb, even though that's where the photons came from, because the photons from the light bulb, the rays from the light bulb that were ordered on their way to the book, they get jumbled up as they leave the book. So you can't see the light bulb in the book. You don't get a reflection in the book because it's not maintaining that order. The mirror does maintain the order, so you can see the book in the mirror because the photons coming off the book maintain their order as they travel to you, and you can see that order. Your brain then knows the shape of that book. Remember, of course, that rays are going everywhere all the time. The photons that hit that book are being sent off in every direction. It's diffuse reflection. So they're going off literally in every possible direction. And that means that if you were going to draw all the rays, it would just fill up your entire page. It'd just be one big black splotch because it would just be rays in every possible location. That's not useful. You can see I've added a couple of extra rays here. I've added an extra grey set and an extra yellow set just to indicate some of the other possibilities. In reality, there'd be a lot more rays than that. There would be essentially infinite rays coming off the book and bouncing off the mirror, but that's not useful for us. So what we tend to do is we choose a few of the rays that are seen by our hypothetical observer. I've drawn a little eye to represent the observer. You don't always have to do that, but I've drawn a little eye to represent the observer, and I've chosen a few rays, just 3 in this case, to represent the path of that light coming off the book, bouncing off the mirror, staying ordered and hitting that eye. So by just choosing a few, you can demonstrate the idea of the path the photons are traveling. But it's important to remember that every single part of this book, every tiny little bit of its surface, is reflecting photons in every possible direction. And the ones that do happen to hit the mirror will be reflected while maintaining their order. They'll undergo specular reflection, and therefore they can be seen if you put your eye anywhere in the right position. So you could move the eye down to this yellow set of rays and they would still see the book because they're still seeing that reflected specular reflection ordered rays there, or go up to the grey and you still see anywhere in between. So there are literally infinite rays you could draw, but don't. Just draw a few and generally choose a hypothetical observer, whether you draw their eye or not. Choose a hypothetical observer and use them to just choose a few of the rays that they would see. If we're looking in a mirror, so as I said, we were going to talk about mirrors, and that's where we're starting now. If we talk about, or we've been talking about mirrors, but we're going to talk about specifically the idea of observing something in a mirror and talking about some of the numbers involved. If you look at a mirror, at an object in a mirror, and that object is the same distance from the mirror as you are, then by basic geometry, the light ray must bounce exactly halfway between the object and your eye. Right? If the distance from your eye to the mirror is the same as the distance from the object to the mirror, and if we know that that angle of incidence has to be the same as the angle of reflection, then the only possible path for that light is that it bounces exactly at the halfway point. So it travels up halfway to the, halfway up, hits the mirror, same angle of reflection off, and travels up to your eye, and that's how you see the object. When we draw a ray diagram like this, you should still be remembering that just like in the previous slide, we still have photons going off in every possible direction from every point of this object. Every point of this object is sending photons off in every possible direction. We are only bothering to draw the one that this person sees. And I've only drawn one this person sees. You could add a couple more. You could draw one from the top of the ball that would bounce slightly higher than that and hit their eye as well. One from the bottom of the ball that would bounce slightly lower and still hit their eye. So you would choose ones that the observer sees. But in this case, I've just gone with a single ray that they see. If you move closer or further away from the mirror than your eye is, then the position that ray bounces still has to adhere by the law of reflection. You still have to have that angle of incidence being equal to the angle of reflection. But the position where it bounces, the vertical height where it bounces off the mirror, will now be changed, because if it's further away, then it's going to have to travel further before it hits the mirror and then less distance after it hits. If it's closer, it'll travel less distance before it hits and more after it hits. And so again, by geometry, we know that where the light ray bounces is going to change around. In this course, we're not going to do much in the way of maths for this kind of scenario of moving the horizontal distance. We're generally just going to talk about basic scenarios of having the observer and the object the same distance from the mirror, because that keeps the maths simple, and our focus in this course is on the physics, not on the math. When you look in a mirror, whether it's at yourself or something else, what you are seeing is a reflection of the object, but it looks like there's actually an object there. If there's a big mirror, then and you see something in the mirror, it can sometimes be hard to tell if that's a real object through the surface or a reflection of something on the other side. Yeah, that's a common trick in movies, and especially horror ones, where you have a mirror maze or something and you can't tell if you're looking at the actual object or a reflection of it. And because of that, because this idea that the reflection looks like a real thing inside the mirror, we call it a virtual image. There is nothing actually there. There's nothing inside the mirror. There's probably a wall and something else on the other side that you're not seeing at all. But what you've got is this idea that it looks like there's something in the mirror. Right? And so what we have is this idea of a virtual image. And as I said, virtual because it's not really there, image because it looks like it is. And so what you have with a flat mirror is this virtual image that is the same distance, the same size and the same distance from the mirror as the real object. And so you can always sketch that onto a ray diagram. Sometimes we ask you to, some of the past exams and things, you'll notice that this is a question we ask occasionally, being able to draw the virtual image on. So again, not actually there, just looks like it is. How do we figure out where to put it? Well, we already said if it's a flat mirror, we know it's the same size. We know it's the same size as the real one, and we know it's going to be the same distance. So even without the rays, we could draw it on anyway. But what you can do, if you weren't sure of all of that, is you take the rays that you actually see, the ones that have been reflected, the ones that hit the observer's eye, and you trace them back into the mirror, into that space where they never actually went, but you just trace them back in a straight line, because that's what our brain processes them as having done. Our brain just thinks that light rays come straight from wherever they originated. They don't, our brain doesn't always process the mirror part very well, and that's why sometimes you think there's something in that space, even though it's just a reflection. So our brain is just tracing that path back to where it came from. And same thing with the other rays. So again, I've just drawn three, one from the top of her head, one from the hem of her shirt, and one from the bottom of her foot. And you can just trace that path back into this virtual land inside the mirror. And if you travel at the same distance as the ray originally traveled, so that incident ray was that long, make the imaginary ray the same length, but continuing along the path that the reflected ray was, and where it stops, that's where that item is in our virtual image land. Right? So that's what a virtual image is. You should be able to hopefully just remember that it's always going to be the same size and the same position if that's a flat, straight mirror. How big a mirror do we need? Hopefully what you've noticed is that the mirror only actually needs to be half as big as the person observing themselves. If you look in a mirror, then the ray that comes from the very top of you and hits your eye will bounce halfway between your eye and the top of your head. And so you actually only need the mirror to go that half distance, so halfway from your eye to the top of your head. And likewise, the one from the bottom of your foot to your eye only needs to travel halfway, only needs the mirror to go halfway from your eye down to the bottom of your foot. So we're going halfway in each direction, and that is half of your total height. So in order to view yourself or to view anything at the same distance from the mirror as your eye, you only need a mirror that's half as big as the thing you're viewing. Feel free to spend a bit of time on the maths and the geometry of that. I've just told you it's half of her height, but feel free to have a little play with that if you don't quite believe me or you just want to convince yourself. As I said, that works for straight flat mirrors. We're not going to go into the maths of curved mirrors because, again, it's just getting into maths and we're focused more on the physics. So as long as you can understand why these things are true, that's the key point here. If you look into a mirror that is curved away from the observer as per part A of this image, then the object will appear to be smaller and closer to the mirror. And that's because if you continue those reflected rays back into the mirror land, right, then they will all meet. They'll make the image closer to the surface than the person is actually standing. And likewise, if the mirror is curving towards them, as per part B here, then the image will appear larger and further away. So it just tricks our brain into thinking that those light rays have traveled from different locations. You don't need to worry too much about how that works. It's as much psychology as it is physics for the interpretation of it. But the light rays, certainly you can continue those pathways back into it and see where the image would end up. As I promised, we're going to talk about rainbows. We're going to talk about how rainbows arrive from refraction. But in order to understand that, we need to understand refraction as it applies to light. We've already talked about light, waves in general and refraction, and the idea that a wave, if it's got two different speeds, it will curve towards the slower one, right? It'll curve. So we saw a sound wave that would curve up from the ground or towards the ground, or a water wave that would go sideways if it was in an uneven pool, things like that. We also said light waves travel slower in different materials. We said that the speed of light in glass is only 2/3 of that it is in a vacuum. In water, it's about 3/4 of what it is in a vacuum. So if a light ray travels into one of these other materials and travels a bit slower, then it will bend as it does so. Unlike the waves that we saw where we talked about this sort of this curving of the wave, for a light wave, because we've got this sudden change from being at one speed to being at a different speed, we get a sudden bend. So we get a kink, an angle, or just a sudden change in direction, rather than this gradual curving that we saw with those sort of temperature gradients and things. So refraction for light, we're generally talking about this kind of idea that it just bends immediately as it enters this material. Because it travels slower in the glass, what that means is that when the incident ray comes in, so incident and reflected are exactly the same as we just saw for mirrors. The normal is exactly the same idea as we saw before, but in this case, we extend the normal into the material so that we've got the normal going through on both sides. The incident ray, if you continue that incident ray where it would go if that glass wasn't there, then for a slower material, that ray will bend towards the normal. That's always the rule, right? When it's slower, it always bends towards the normal. We'll talk a bit more about understanding that in a moment. But that's what I want you to remember. You've got an incident ray and reflected ray just like before, but you also get this refracted ray, which is the ray traveling through the object. And because it travels slower, the ray bends towards the normal. So you need that ray to be closer to the normal. When it goes from a slower object back to the faster one, it's going to bend away from the normal, exactly the opposite. If it's going into a faster material, it bends away from the normal. Some people remember that by just remembering the phrase speeds away. Speeds away. If it's going into a faster material, it will move away from the normal, speeds away. So that's the idea of refraction. Light will bend towards the normal as it goes into a slower material and bend away from the normal when it goes into a faster material. So what that means is that if you have, as per this diagram, a light ray traveling in air, hitting a glass block, bending towards the normal, continuing through the glass block, and then coming out of the glass block, bending away from the normal, the amount it bends towards the normal and then away from is exactly the same. So that the angle that this outgoing ray makes as it leaves the glass block is actually the same as the angle the incoming glass block makes with that normal. So that incoming angle, the incident angle, and that final outgoing refracted angle is exactly the same. You'll notice that it's not in line with, because it changed course because it went through the glass at a different angle, it's not in line with, but it is parallel with that original incident ray. So those angles are all exact, they're all known angles. This leads us to another type of virtual image. We saw with mirrors, we had a virtual image because we had an image that wasn't actually an object in that place, and that it was in a different position from the real thing. Indeed, that's how you can view yourself, because your image ends up in a different place from you. Again, our brain does the same thing, and it views the object as being where those rays seem to have come from. And so the example here of a fish underwater, the light rays travel up, they bend as they leave the water, and then a viewer sees them. That viewer's brain processes those rays as though they didn't bend, as though they just continued in a straight line. And that would make the fish appear to be higher up than it actually is, in a different position. So again, we're seeing a virtual image. In this case, you can't see the real image, the real object. Right? You can't see the real object because you can't see it being at that exact location. You can only see this virtual one being where your brain thinks it is, even though it's not. That leads to all sorts of interesting scenarios, such as this photo that I shamelessly stole. I can't remember if it's from the textbook or just online, but just the idea of refraction. Here we've got light rays coming directly from the physicist's head and hand and sheet of paper directly to us. So those are not refracted. They're just traveling straight from them to us. The light rays coming off the rest of the physicist underwater are being refracted. They're traveling some of the way underwater, and then they bend as they leave the water until they meet the camera lens. And that means that they look like they've come from a different location. In reality, of course, we know that his body is underneath his head. That's how humans work, right? His body is directly under his head. But to the camera and thus to us, it looks like his body is in a different position. Right? That is a virtual image. What you're seeing is the virtual image versus the actual image of his head. I say image because it's still not actually him. You're still looking at a photograph. This idea of refraction of light, I see it just a sudden kink. I will now clarify that and say that it's a sudden kink when the material suddenly changes. The atmosphere of Earth actually fades in a sense. From being nothing out in space, you get thin atmosphere, and then it gets thicker and thicker as you get towards the Earth. And in that case, you actually get a bending of light rather than a sudden change, because you don't have a sudden change in material. But what that means is that the sunlight, as you get towards dawn and dusk, where the sun is now traveling through a lot of atmosphere, the sunlight will bend a lot more. And then the result of that is that the light ray appears to be coming from a direction higher than the sun actually is. So when you watch the sun set, it's actually already set as you watch it set, right? It's already below the horizon in terms of the geometry of the scenario. It's just that the light is being bent towards you, so you can still see it even after it's below the position where you would expect to be able to see it. Now, I don't expect you to memorize this or pay too much attention to it. It's just a fun little bit of information, not really part of the accessible material, but certainly, again, something you can understand, and an everyday occurrence of everyday evidence of this phenomena. So we've already met angles of incidence, angles of reflection, and now we have angle of refraction. Angle of refraction, exactly the same, still measured with normal, still measured against the normal, but remember, as I said, the normal continues into the object now, not just on the outside of the object, but it's still exactly the same. Angle of incidence is the angle between the normal and the incoming ray. The angle of refraction is the angle between the refracted ray, the one traveling through the object or through the new material, and the normal. That will be the same normal because the point where the incident ray hits is obviously the same point where the refracted ray starts. So that is the same normal line. It just continues in and out of the different materials. So those two angles, theta I and theta R. For reflection, we had the two angles being exactly the same. The incident and the reflected rays are the same. That's the rule of reflection. For refraction, they are different. We've already talked about that. Different materials means it'll bend towards or away from the normal based on the speed. That speed is given by the refractive index. So we've already kind of met this concept because we said that the speed of light in glass is about 2/3 of that it is in a vacuum, and in water it's 3/4, and so on. The refractive index is how we record that bit of information. So the index of refraction is the ratio of the speed of light in a vacuum over the speed of light in whatever material you're looking at. And again, this depends entirely on the material, and it varies for all the different materials. And so the only way you can really get this information is to look it up, just like we've seen with lots of things like densities and specific heat capacities and things. There are plenty of times that you need to know a quantity, and the only thing you can do is look it up in a table of data. The refractive index is one of those. Here are some examples. In helium gas, the index of refraction is 1.00004. That means that it's only ever so slightly slower than the speed of light in a vacuum. So it's practically the same. Unless you're going all the way down to 6 significant figures, then you can treat it as being the exact same speed as it is in a vacuum. For air, it's 1.0003. So again, unless you're going all the way down to 5 significant figures, you can just treat it as being the same speed as the speed of light in a vacuum. And that's what we do in this course, and indeed most undergraduate courses. In water, though, it's quite a bit different. It's 2/3 of the speed of light in a vacuum. So that means our refractive index, because the ratio is the other way up, it's the speed of light in a vacuum over the speed of light in the substance. It comes out to be 1.33 for vegetable oil, about 1.47 for glass. It varies, but again, around about 1.5. And diamond is the slowest with a refractive index of about 2.4. So the slower speed of light results in a larger refractive index. So those bigger n values mean that the light is traveling slower. It's traveling slower, it's got a bigger n because it's going to bend more. This n is an indicator of how much that light is going to bend as it enters the material. So light traveling from a vacuum into air is barely going to bend at all. 1.00003, or I think I've said one too many O's, but it's barely going to bend at all. But light traveling from a vacuum into vegetable oil is going to bend a significant amount because we've got a refractive index of 1.5. And going into diamond, it's going to bend even more than that because we've got a refractive index of 2.4. The way we calculate that exact bend, what the new angle is, that new refraction angle, is using this formula called Snell's law. And it's quite a simple formula. It's just that the refractive index of the incident material times the sine of the incident angle is equal to the refractive index of the refraction material times the sine of the refraction angle. So Ni sine theta I is equal to Nr sine theta R. That's the formula. That's how we know what that angle is going to be. Again, you already should know, just looking at a scenario, whether it's going to bend towards or away from the material, from the normal, sorry. And again, you can remember speeds away if that helps. Faster speed of light means it'll bend away from the normal. Slower means it'll bend towards the normal. And then you can use this formula to find that exact angle. But I still really thoroughly recommend, as I've done right throughout this course, that when you look at a scenario, you instantly make some kind of little assessment. And you say, right, it's traveling from air into glass, that's slower, it must bend towards the normal. And that way, when you do your calculation, if you get theta out, theta R, and it's greater than theta I, you instantly should know, hold on, that's not right because I expected it to be less. And so it's just a really good little double check. So getting an idea of an intuition almost about what that light ray is going to do. There is a principle called the principle of least time, which personally I'm not a huge fan of, but some people do find it's another useful way to think about these sorts of scenarios. Personally, I'm happy just thinking about the idea that the slower light is going to bend towards the normal because we know that the light bends. That's the point of refraction. It bends, any wave bends as it changes speed, and we know slower will bend towards the normal, faster will bend away. But the other way that you can think about it is that the light will take the quickest path. Because it's traveling slower through the glass, it wants to spend less time in the glass. Right? I use the word wants very cautiously because obviously it's a light ray, it doesn't have any desires. But it wants to spend less time in the glass, so it bends towards the normal in order to spend a bit less time and get through it a bit quicker. And then when it bends out again, it can speed up and go more directly to where it's trying to get to. So it results in this sort of zigzag path. So it's the same reasoning, it's just a slightly different way to think about it. And the analogy that is used a lot for this principle of least time, which again, some people find helpful, is to imagine a person as a photon. In this case, a lifeguard. Someone is in the ocean. The person in the ocean that they're trying to rescue needs help, and the lifeguard wants to get to them as quickly as possible. If they could run and swim at the same speed, then they would just aim directly for the person because that's the quickest path. We all know that the shortest path between 2 points is a straight line. But if we want to minimize the time to get there, and they are quicker on the sand than they are on the water, if they run on sand quicker than they swim in the water, then they would want to spend more time on the sand and less time in the water to minimize the time it takes to get to that person. And that would result in a diagram like that on the left here, where they run at an angle towards the water and then change their angle as they enter the water because they're now traveling slower and they want less time in the water. And you can see that that results in less distance through the water than the direct path did. On the opposite side, if they actually swam quicker than they ran on the sand, then they would run directly towards or more directly towards the water and spend less time on the sand and then swim directly towards the person at a different angle and spend more time in the water. So it would be based on the different speeds in the two scenarios. And so this least time analogy does help some people get to grips with this concept of the light photon traveling the path that is going to be quickest for it. But as I already mentioned, the light has no choice. It doesn't have any wants or desires. It does not get to decide how to get to its final destination like the lifeguard does. So the light ray is just doing what it does because of the physics involved. The principle of least time can help you figure out what that path is going to be by imagining what a sentient thing, something with desires or decisions would do if it was in that scenario. But it's important to remember that the light ray obviously does not have a choice, right? It doesn't have a choice. The physics determine the result. In a vacuum, light travels at the same speed of light, right? That travels at c. Remember, c was almost 300 million meters per second. It travels at c anywhere. All light waves do that, regardless of if they're a radio wave, microwave, visible, gamma, whatever. They all travel at that same speed. But when you get into a medium, any kind of material, so the idea of traveling through air or through water or through glass, when you travel through those different mediums, the speed now depends on the frequency of the light, not just on the material. Remember that the electrons in the medium are oscillating because of the wave, and that creates a secondary wave which interferes, and that's why the wave slows down. So that means a light wave that's traveling with a different frequency is going to cause a different secondary wave, and it's going to cause that slightly different interference pattern, and you're going to get the slightly different speed of light. You don't have to remember all those details specifically, but what it means is that the speed of light of different colors in glass or in water is going to be slightly different. In a vacuum, all exactly the same, but as soon as you get into a material where they travel a bit slower, the different colors will slow down slightly different amounts, just slightly. But it's enough that they bend slightly differently as well, because remember, the speed of the light in the material determines how much it bends. So what that means is that violet, which is vibrating the most, has the highest frequency, will slow down the most because it's getting the most interference from those electrons in the material. So it will bend the most. So if it slows down the most, it bends the most. That means that violet will bend slightly more than red. Red will bend the least because it's at the other end of the visible spectrum. And all the colors in between will bend slightly different amounts. So purple will bend the most, or violet. Blue will bend the next most, and then green, and then yellow, and then orange, and then red. So they'll all spread out as they bend into the glass. So we know if we have a white light ray, remember that's all the colors at once, coming into the glass block, they'll spread out. And as it bends into the glass block, the red will go one way, but the violet will go a bit further around, and the colors will spread out. And that is called dispersion. Dispersion is the spreading out of the light because the different colors have slightly different properties. Not hugely different, but enough that we can see that result. And in the classic example of the prism where the white light spreads out into a rainbow, we actually have dispersion occurring twice. Once as it goes into the block, and again as it comes out of the block. Notice that we use a triangular prism. Again, we're not going to get into the geometry. We're not going to talk about all the maths behind this because it gets a bit more complicated. But if it was a rectangular block where the in and the out sides were exactly parallel, then it would spread out as it goes in, but then it would unspread out as it leaves again. By having a triangle like this, it actually spreads out both times because of the angles involved. And so that's why we use triangular prisms to try and force that dispersion to get that rainbow occurring. That same process can happen in water droplets. Water droplets are nice little spherical droplets. They're perfectly spherical because of surface tension, a property of liquid. They are perfectly spherical. And what happens is that the light does the exact same thing as that prism did. It spreads out the different colors as they enter, as you can see at the top of this diagram. So white light coming in, it spreads out. I've only drawn 3 different rays on here for simplicity, but it's obviously all the different frequencies, all the different colors will all spread out. But we have the red ray bending the least, the purple ray bending the most, and all the others in between. But what happens in a water droplet is you actually get a reflection on the inside. We're not going to go into the details of why. It just turns out that the way the angles work is that you get this extra, the angle it hits the inside of the water droplet at is the right to reflect in rather than refract out of it. And so you get this reflection inside, and as they bounce off the inside and then they approach the another part of the inside of the water droplet, they refract again on the way out. And so what happens is that these light rays spread out as they're going in, and they spread out again as they're leaving. And so the white light comes in at the top, in in one direction, and it actually comes out in a similar direction, so on the same sort of side of the water droplet, but now all spread out. It disperses those colors very well. And that is what rainbows are. Rainbows are just the sunlight doing that to a whole bunch of water droplets up in the clouds or just in the sky. Sometimes you can't even tell that there are clouds there. They might be quite spread out water droplets in quite a faint rainbow. The denser the water droplets, the more obvious the rainbow would appear. But that's all that's happening in a rainbow. The sunlight is hitting all these water droplets. Remember, the sunlight is everywhere all at once on Earth. If you're on the sunny side of Earth, if it's daytime, then photons from the sun are just hitting everywhere all at once. And so if there are water droplets at the right location, then the sunlight will hit them, bounce, they'll refract as they spread out, as they go in, reflect off the inside of the droplet and refract again as they come out and come towards you, now all spread out. Now it's important to realize you're not seeing all of those spread out ones from the same droplet, because of course they'll be spread out. By the time you see it, if you look at that droplet, you're only in position to see the specific color from one of the droplets, not all of the colors from that one droplet. If you could see all the colors from that one droplet, that droplet would just look white, right? But it doesn't. It looks one specific color. In the case of this top droplet, it looks red. And so you'll get this whole row of droplets that all look red. They all look red, and they end up forming a sort of a circle shape, right? And that's why rainbows look like a big arch, because the geometry means that all the ones in that circular path all have the same red color. And you go down a little bit, all of those droplets, you're in the right position to see them as a slightly oranger red, right? A slightly different color of red. And then the ones below that, slightly different color. And of course, you're seeing heaps of these raindrops. You're not just seeing a few of them. You're not just seeing 7. You're seeing heaps of them. And so every one is just a slightly different color from its neighbor, going from red all the way through the colors of the rainbow through to the violet. And so when you look at it, that's what you see. You see each color as being, each raindrop as just being one color, because it's spread out the light and you can only see one color from it, instead of being white like you see with normal clouds. And that's all that rainbows are. The diagram here is exaggerated. They've got neighboring droplets showing red and then violet. Obviously, that's not how it really works. You get millions of droplets with one being red, the next one being a slightly different red, and then so on towards the orange, and then yellow, and then green, all the way down to violet. But for simplicity, they have shown they've just shown 2 neighboring ones. As I mentioned, the geometry of that means that what you're seeing is sort of a circular shape. And indeed, you're actually seeing a bit of a cone, because the light hitting the water droplets a bit closer to you will reflect and refract at the right angle as the same ones as ones a bit further up, getting light a bit further away. And so it sort of ends up being a cone of light. Not too important, but the cone that you see is quite deep, not just one layer of droplets, right? What is kind of important, not for any real scientific sense, but just one out of fascination in my view, is that no one else sees the same rainbow as you. No one else sees the same one, because where you are standing, you are intercepting the photons of one specific color from a water droplet. No one else can intercept that photon from that water droplet because you're doing it. If they see that same droplet, then their eye is at a slightly different angle and they're going to see a slightly different color from it. And then the same for all the other ones you see. So the rainbows might be very similar, but they will technically be slightly different, because you're all seeing a slightly different photon from each water droplet, because you're only placed to get one color from each water droplet. So that's rainbows. The next part of this course, as I said, is on lenses. Lenses use this concept of refraction and build on that a little bit. When we talked about a prism, so dispersion, we talked about the idea that it spreads out the different colors. But what about if we just stick with white light and prisms? What that means is that the path the light can take, so let's just choose one frequency so that we don't get any dispersion. So let's say we just shine a yellow photon through this prism. If you send a bunch of parallel yellow photons through, they're all going to bend different amounts, and they're all going to come out at different positions, right? Different to where they went in. In fact, if you set up the right prisms, you can actually make light do U-turns and all sorts of things. So you can do lots with prisms, but we're not going to talk too much about prisms. What we are going to talk about is the idea of setting a specific one up so that you get a light ray going straight through. If it goes horizontal, it goes straight through, but the further up the light ray goes, then it bends and it comes out so that they all meet back at one point. So hopefully you can imagine how that would work. If this light ray hits a perpendicular surface, it's not going to refract at all. It's already on the normal. If your angle of incidence is 0, then your angle of refraction must be 0. It doesn't matter what the refractive indices are. N sine theta equals n sine theta. If sine theta is 0, it must still be 0 here. There's no way that the n's can change that. So if you have a perpendicular surface and a light ray coming in, it's going to come out perpendicular as well. So a perpendicular light ray will always go straight through. But by the time you go up to the next light ray that's drawn on the diagram, you've now got a slight angle and you are going to get some refraction. Right? The next one, you've got an even bigger angle. So that means a bigger angle of incidence. So the bending is going to be proportionally slightly more. And the point is you can set it up so that the light ray, in this case, if they're all coming from point A, that they all end up traveling horizontally through this prism, which is actually a lens, which we'll see in a moment. And then when they refract out, they come back out at that same angle because you make it a mirror image, a symmetrical shape. I shouldn't use the term mirror image because we're not talking about mirrors at the moment. So you make it a symmetrical shape, means when it comes out, it bends the same amount again, and they all meet back at point B. And so it doesn't matter which path they all take the same time. So that principle of least time means that it doesn't actually care which path it takes, and all of those paths all end up back at point B. This kind of lens is called a converging lens. Converging because incoming light is all bent to meet at a single point. And you might do it like I just showed you, where it starts at a point, bends and comes back to a point, or you might do it so that parallel light, like the sunlight, remember sunlight is coming in parallel, sunlight all meets at one specific point, right? And that's a converging lens. This type of lens is convex. That's just the name of the shape. When you have two curved surfaces that curve away from each other, that's called convex. You can do the exact opposite though, and make the lens be concave, which is where you've got two curved surfaces going in towards each other. That is concave. If you have a concave lens, then what that means is that the light rays are going to be spread out rather than bending towards a point. They're all going to bend away. They're all going to bend away from a point. And that's a diverging lens. So convergent and divergent, they're relatively familiar words for most people. If they're not, just take a moment to memorize those: convergent and divergent, or converging and diverging. As you'll see on the diagram though, these dotted red lines show you that parallel light coming in, again like sunlight, will be spread out. But the way that it gets spread out by a diverging lens, if you make it correctly, is that it looks like it all came from a single point. So it spreads the light out, but it looks, if you trace the paths back, they all meet at a single point. That single point is going to be important. That's why I'm just pointing it out now. And so here's this same diagrams, but well, different versions of the same diagrams. Showing both. On the left, we've got converging with a convex lens, and on the right, we've got diverging with a concave lens. There are a bunch of terms to memorize, unfortunately, with lenses. I'm not a big fan of just rote memorization, but sometimes there's no real alternative, and you do need to just learn some words. And the ones here are principal axis, which is just the line joining the centers of curvature of the lens surfaces. There is a diagram on the next slide, so don't fret too much. I'll repeat these on that slide. The focal point, which is the point at which incoming light parallel to the principal axis will focus. So remember how we said it all comes to a point? That's called focusing, and the point at which it does that is the focal point. The focal plane is the collection of all possible focal positions for light beams not parallel to the principal axis. You actually don't need to remember that specific term for this course, but if you are interested in lenses and light and optics, then it is a useful one to be aware of. But that's just saying because light doesn't have to come in parallel to the principal axis, then you may get a scenario in which the light is coming in at all parallel to each other, but not parallel to the principal axis, and that will focus somewhere different. And that, if you do that for every possible angle of incoming light, all those points traced out make a line, and that is, or they make a plane technically in 3 dimensions, and that is the focal plane. As I said, you don't need to worry about that for this course. Focal length is the distance from the center of the lens to the focal point. I said either focal point there because you can obviously shine light on either side of a lens and it will do the same thing because lenses are always symmetrical. At least the ones we're dealing with are always symmetrical. Center of curvature, we've already talked about the idea that a concave or a convex lens is kind of like two curved surfaces. And those curved surfaces obviously have a radius, and you could continue that curved path and draw a whole circle. And if you did that, the radius of that whole circle is the radius of curvature, and the center of curvature is the center of that whole circle. So that's just talking about the geometry of the lens itself, essentially. So here's a diagram just showing those. We've got the lens itself in the center. The principal axis you'll see is basically the one that goes straight through. Remember the idea that you've got a perpendicular normal, the bit where that is straight through the middle of the lens, that is the principal axis. The two focal points, one on either side, and the focal length being from the center of the lens to those focal points, either one. And then the center of curvature, you can imagine if you continued this circular arc that is one side of the lens, if you continued that on, it would make a big circle, and that center of curvature is where the center of that circle would be. Now we're going to stop talking about lenses for a moment and talk about seeing objects again. We've already talked about the idea that when you see an object, you need to see the order. You need to get that ordered array of photons coming towards you from the object. So when you look at the object directly, all the photons coming off it are obviously ordered according to the shape of that object. But if you look at, for example, the wall in this diagram, we've got a stack of 3 blocks and then we've got a wall. The photons coming off the blocks hit that wall everywhere. And everywhere that they hit it, they undergo diffuse reflection and they spread out everywhere. And so we can't see any kind of image of that block. We can't see the block reflected in the wall because there is light from every part of the block hitting every part of the wall. So it doesn't help us see the blocks. But what about if we put another wall in between them and we put a tiny pinhole in that wall, in that in-between wall? Put a tiny hole in that in-between wall. What's going to happen now is that for every part of the original wall, which is now in the dark because there's no other light source apart from this tiny little hole, every other part of that wall is going to be dark because there's no photons hitting it. But every point on that wall where there is a photon hitting it, it will only be from one spot on the block, and that's the point that is directly opposite it through that pinhole. So if you start at the very bottom left of our red block, it'll travel through the pinhole, and then it'll get up top right of our image. And the same for every other point. I've drawn 6 example rays on there. Obviously, there would be many, many more, infinite more, filling in the entire image. But the idea is that the photons that leave the block, they might spread out and hit that wall everywhere, that white wall, that first wall everywhere, but only a single ray from each location on the block can travel through our tiny pinhole and travel through to the second wall. So even though the photons that travel through that pinhole and hit the second wall undergo diffuse reflection and spread out everywhere, our brain is only seeing photons from a single part of the block on each part of that second wall. And so what we see is an image. So we see an image of the blocks. And this is a real thing. You can set up a pinhole camera. It was developed a long time ago. It was used for painters and artists before we had any kind of real image capturing devices. And by setting up a room with a tiny hole for entry of light and no other light source, so they make the rest of the room dark, they could get this image, a temporary photograph for them to see and look at, and they could basically copy that into their painting with having a nice simple image to look at rather than having to look at the real world. It's just a bit easier to measure and refer to some things that way. So that's a historical context, which you don't need to know. So it is called a pinhole camera, as I said. You may also have heard of it as the name camera obscura. The problem with the pinhole camera is that the hole needs to be really tiny. It needs to be so tiny that you're essentially only letting a single ray through from each location on the object. And that means you get a very dim image because you only get a single ray from each location, a single stream of photons for each location, and you get a very dim image. If you make the hole a little bit wider so that more rays can get in, then the image does get brighter, but it also gets blurrier because now each part of the wall can actually get rays from different locations in the real world. So these different locations can now hit that one spot, the image gets blurrier. So instead of restricting the paths of light like we do with the pinhole, lenses were developed, and lenses take all of that light and focus. Remember the focal point, they take that incoming light and they bend it and point it all at one point. They focus all of the light that hits the lens onto a single spot. And so by using a lens, you can actually keep an image focused, not blurry, but also let a lot more light through, as much light as the size of the lenses. So if you made a lens this big, all of the photons that hit this lens will now be focused onto one specific point, instead of needing a tiny pinhole that only lets those photons go through to that specific point. So that's what lenses do. They're a great advent, obviously, and they've allowed a lot of other technology to build on top of them. When we use a magnifying glass, which is just a converging lens, that's all it is, and you focus the light from a small object so we can see it clearly as though it were bigger, then this is just the same as seeing that underwater fish or seeing the physicist in the pool. It bends the light and makes it look as though it comes from something else, from a virtual image. Makes it look like the object is in a different position and indeed a different size. So when you look at something through a magnifying glass, if you focus it correctly, the object will appear crisp. It won't be blurry, but it will appear bigger and further away than the original. And so because it appears bigger, you can see it more clearly, and that's how it helps people as their eyes start to deteriorate. They can still read small text using magnifying glasses. That was a virtual image. Remember, virtual images aren't really there. They're our eyes seeing the light directly from the object as though it was somewhere else. We've also now got this idea of a real image, and we actually met the idea of a real image with the pinhole camera. So I'll go back a few slides. This pinhole camera, these three blocks that we're looking at here, the reflected ones, the ones that are on the dark wall, that's a real image. So a real image is one that the image itself appears on a surface and anyone can see it. Remember that a virtual image is just how the observer sees the light rays from an object. A real image, though, is something that is there regardless of the observer. Right? That image is there regardless of anyone's looking at it, and if lots of people are there, they can all see it. That image is actually there. It's a real image. And with a lens, we can create virtual images, like with this one. In this case, you'll notice the object is between the lens and the focal point. Right? So it's in between the two. You'll get a virtual image that's bigger, and that's how you can see better. If you instead have an object further away from the focal point, then you can do what the camera obscura does, or the pinhole camera does, and you can create a real image upside down on the wall. You can create a real image. And that's the exact same principle as we saw with the pinhole camera. So that's a real image, because regardless of whether anyone's observing it or not, or if lots of people are, they can all see it. That image is actually there. Those photons are actually bouncing off that surface at that moment, or constantly, if the image is there. They're constantly bouncing off that surface. So anyone that looks at that surface will see those ordered photons coming off the surface. We do need to be able to draw lens diagrams for, ray diagrams for lenses. We've already met the terminology, we've already met the idea of doing rays. The trick here is that we draw 3 different rays. 3 is common, you could draw more, but 3 is the baseline, and it's the simplest to just draw 3. First thing you do is you draw your principal axis, your lens, and your object. The lens we draw as a single vertical line. You can sketch on the shape of the lens if you want, but always make sure you include the vertical line as well. So you get your principal axis, which is your horizontal line, your lens, which is your vertical line, and then you draw the object. Right? The object can be wherever it actually is. Normally, we'll just draw it standing up on top of the principal axis for simplicity. You also need to mark on the 2 focal points. And generally, when you draw a lens diagram, you should draw it to scale. Sometimes you might just want to sketch it to get a rough idea, but if you can, I recommend using a ruler and actually drawing it to scale, because it will work, and you can just measure the result off to scale as well and get it that way. What you want to do is draw 3 different rays. The first one goes straight through the center of the mirror and it won't refract. In reality, it does a little zigzag. Right? It does a little zigzag, but because the lens is quite thin, remember how we said that the incoming ray, if it refracts through like a block of glass, the incoming ray and the outgoing ray are at the same angle, but they're actually slightly shifted, but it's parallel. because the lens is usually pretty thin compared to the distance it's traveling, we can neglect that essentially. We can just draw it straight through the center and ignore the fact that it would shift slightly and be parallel. So we draw the first ray straight through the middle. It doesn't refract, and we just get to go from the top of the object right through the middle, and you just keep drawing. At this point in time, you won't know where that image is. So you just keep drawing that line for a bit. You're not sure how far it'll go, but you just draw it on for a bit. The second ray is one that goes parallel to the principal axis. So that's the top of those three rays coming off the object, goes across through the top, hits that lens line, the vertical lens line, and from there, because it's coming in parallel, that means it's going to be focused onto the focal point. So you can then draw it through the focal point and keep going. And at that point, you'll see where that and your original line coincide, and that is where the image is going to be. And then you draw another one going from the top of the object through the first focal point, and that's just the opposite of the first one. If it's going through the focal point, that means it must go out parallel. Right? That's how lenses work. If the light ray comes in parallel to the principal axis, it'll go through the focal point. If it goes through the focal point on the way to the lens, it'll come out parallel. That's how lenses work. And so we use that idea to draw our ray diagrams. I'm not a big fan of just telling you to learn some method, as you hopefully have picked up from this course. I prefer to really explain the concepts and stuff. For lenses, I've given you a bit of an idea of it, but unfortunately at this point, I'm just going to tell you to learn this method, right? Draw on the lens, draw on the two focal points, and then draw on these three rays. All from one point on the object, usually the top, all from the top of the object. You draw one straight through the middle of the lens, one parallel to the principal axis, and then through the focal point on the other side of the lens, and one through the close focal point, and that comes out parallel. And if you draw it correctly, if you draw everything to scale and you have the focal length measured on correctly, then what you'll get is all three of those rays converge, they meet at a single point. And that single point is where the image is going to be for the point where your rays started on the object. So if you start at the very tip of the arrow, as per this example, then where they all meet will be the very tip of your image. Now, as I said, I've just drawn those three rays, or I stole this image, I think, from somewhere, but we've drawn those three rays as coming off the tip of the object and meeting at the tip of the image. You could do the same thing and start at the halfway point of the object, and that would all focus at the halfway point of the image. It's important to know that's going on. It's not really necessary to draw that for every single part of the image, or again, you'd be drawing infinite rays. Right? It's more useful to just draw three rays starting at one of the extreme points of our object and use that to see where the extreme point of our image will be. But just to reinforce what I was just saying, I'm going to just quickly do another one just by hand. This is not going to be to scale, despite what I was just telling you. So here's our principal axis. Here's our lens. And we're going to have a focal point of this much. So there's our focal point on each side. And then you draw some object. And what I'm going to do this time is I'm going to draw a nice two circles. Right? Those are our one object. And so as I said, what you would do is you would draw three possible rays. So from here, we can draw one that goes straight through our our center, one that goes parallel and then through the focal point, and one that goes through the focal point initially and then parallel. I didn't quite draw that right. And then parallel. The other thing I'll point out is that rays always need arrows on them. Always have an arrow on your ray, please. So there's our three rays from there, and that means that we know that the very tip of our image is going to be right down here. So that's going to be the tip of our image. The reason I wanted to do this by hand and just expand is to continue what I was just saying about the fact that these image rays are going to be coming off every part of this object, not just that one point. So let's also do it for this point, right? It's from this middle point. If we draw that, again, straight through the middle for our first ray, and then horizontal or parallel, and then through the focal point, and then through the focal point, and then parallel, and then we get that. And so the center, all the light coming off the center of this figure 8 type object would end up focusing here. And the last one is a bit tricky because you don't actually have 3 different rays to draw if you were going to draw it off the bottom. If you're going to draw it off the bottom, you don't like they would all essentially just be straight lines, because one of them going through the center is also going through the 2 focal points, so that doesn't help. But I've drawn it slightly above the very bottom, so that we can get a rough idea, and that's going to be very difficult for me to draw, but I'll try anyway. That will go slightly through. This one will go through the focal axis first. I'm exaggerating it slightly for the purposes of demonstrating. And then that one will go there and then through that, and they will meet there. So this little distance here has been increased slightly as well. And so what we get is this idea of, wrong color there, the idea of that, that figure 8 being increased in size. But that is the whole process. Again, I've been naughty, I haven't drawn on my little arrows to represent rays. So you should always have arrows to show the rays. But that's how you draw a ray diagram for a convex lens, for a converging lens. So you always just draw the 3. 1 straight through the middle, 1 parallel, and then down through focal point, 1 down through focal point, and then parallel. And wherever they meet, that is where that part of the image will appear. So as I said, we often just take the very top of our object and use that to find the very top of the image, and then we know that it's basically going to scale. If this is what the image looked like, it'll be flipped upside down, and it'll be that big instead of that big. So that's how we generally do it, but there's nothing to stop you doing it from another point on the object, just to check, well, the middle of the object will appear, yeah, in the middle, as we would expect. How far away is that image going to appear? You can use the lens equation to figure that out. The lens equation tells us that the distance of the from the image to the lens plus, well, I should say 1 over the distance from the image to the lens plus 1 over the distance from the object to the lens is equal to 1 over the focal length. Right? So 1 over di plus 1 over di is equal to 1 over f. And using that equation, you can find whichever of those 3 things you aren't sure about. So you'll often see questions where we say a lens is placed 20 centimeters from an object. The lens has a focal length of 10 centimeters. How far away will the wall need to be to see that image? Because you're only going to see that image if it's focused correctly, which means having the correct image distance for the object and focal lengths that are provided. So you use this lens equation, you just need to be able to rearrange that. So if you're, again, your maths should be at a point where you can happily rearrange equations like this with all these reciprocals in them. So do spend a bit of time, if you're not 100% on that, just doing a few practice questions. Make up 2 of the values and rearrange and solve for the 3rd one. Once you do that, just as a little tip, if you're doing that as a bit of practice, you make up 2 values, rearrange and solve for the 3rd one, put them back into this equation first and make sure your left and right hand sides are the same. That's the only way to check that you did that solution correctly. Diverging lenses produce reduced virtual right way up images, regardless of how near or far the object is. So the convex or converging lenses that we were just talking about, if you had the object between the lens and its focal length, then you would see an enlarged virtual image. That's what a magnifying glass is doing. If you have the object greater than the focal length away from the lens, then you can create a real image on a wall, right? You can create a real image that you essentially project somewhere. For a diverging lens, you cannot create a real image. You cannot. It does not work. The physics don't work because it's always spreading out the rays. There's no way to focus that on a wall if it's spreading out the rays. What they do is they always produce a reduced virtual right way up image. So that means it makes things smaller. So if you look at the right hand lens in this photograph, you can see the whole of that vehicle, whole of those 2 vehicles in the lens, even though the lens overall is taking up less of your field of vision than the 2 cars are. You can see the cars behind it are actually much bigger. So it reduces that image, and that allows you to see more through that lens than you do if you look out at the world normally. So that's the benefit of diverging lenses, but they cannot ever produce real images. We can do ray diagrams for diverging lenses. I expect you to be able to look at this and understand it, but I don't expect you to necessarily be able to draw them. There's nothing to stop you being able to draw them. Right? You have all the information, all the understanding. The one little trick is that we have this exact same three concepts. We have the first ray, A, is going straight through the center of the lens, and that just continues on without being diverted at all. It's not refracted because it's straight through the center. The trick is that the two light rays will never actually go through the two focal points, right? They will look like they were going to. So what you have to do is for ray B, where you start parallel, you then draw it heading directly away from that close focal point. That gives you your second ray. The third one, you draw it as though it's going to go through the far one, but then it refracts and goes parallel instead. So neither of the focal points are actually hit by a ray, but you can trace them back to the focal points to figure out where they are going to be going. Excuse me. And what that allows you to do is the exact same thing as the ray diagrams for the converging lenses, where those three lines all intersect. But in this case, it's the lines that travel back as though that's where the ray had been, even though it wasn't. These gray lines, so travel that B ray back in through the lens, travel the C ray back in through the lens, where they all meet, that's your virtual image. So as I said, it's always reduced, it's always smaller, because you can see if these rays are getting spread out, then they'll be pointing to a location closer than that original object. So it will always be reduced, and it's still the right way up. On the converging lens, we saw that the image ended up upside down based on the light rays. Here you can see the image is still the right way up. And again, we've just taken the very top point. Of course, light rays are coming off all parts of this object, and if you did one in the middle, you would see that that would end up in the middle of the virtual image, and that's how you can see a whole object as per this diverging lens here. So that's a diverging lens ray diagram. You don't really need to be able to sketch that from scratch. As I said, though, there's nothing stopping you. Just that slight little trick that the rays won't go through the focal point. They will travel along the lines that would, but they won't actually go through it. So that's diverging lenses ray diagrams. And that is the end of lesson 36, and thus the end of this course. I do hope you have enjoyed the course, that you have found it engaging and accessible. I'm always open to feedback, and good luck for the final exam.